So hello, welcome to Chapter 10, Example Problems, where we'll go through example problems. You think after all this time I would know what to say to start these things. I always like to talk about what is old exam problems, because the final is upcoming. Fun fact, I finished writing draft 1 of the final today, but it still needs editing and for me to take it and test it and stuff, but it is being worked on. But there will be a problem from Chapter 10. This first problem is an old exam problem. So is the second one. So is the third one. The fourth one isn't. The fourth one's just kind of interesting. And the fifth one is not also. And I don't even know how I'll get to the fifth one. So I'm going to jump right in. Hopefully you already had a chance to look at these. Here we go. So the first problem is about Tiggle. And it says, Tiggle from Winnie the Pooh has a tail made out of a spring that he likes to bounce on. And then I do a whole bunch of references to a song from Winnie the Pooh. Let's say Tiggle starts bouncing and moving back and forth in simple harmonic motion. So he's not like springing in the air as Tiggles want to do, but it's just kind of doing this. I should change this problem to something that actually makes more sense like that. If he's bouncing like this, with a period of motion of 0.8 seconds, and his maximum displacement from equilibrium is 0.2 meters. Okay, let's just write down what we know so far. So we're saying we're bouncing back and forth with a period of motion of 0.8 seconds. And the maximum displacement, that's known as the amplitude, of 0.2 meters. So if Tiggle's body has a mass of 11 kilograms, which is only 11 kilograms because let's face it, Tiggle is a stuffed animal, as are all the people from the 1,000 Acre Woods. Or 100 Acre Woods? I forget if it's 100 or 1,000. What is the spring constant of Tiggle's tail? So I have up here the equations as always, though these are kind of coupled. And we're looking at a spring, which means I can use any of these equations. It's of note also, I could use any of these equations in this box, because there's other boxes for springs and pendulums both. But I know the period, I know the mass, I want the spring constant. And I have a direct relationship. That right here I say the period of any spring is 2 pi square root of m over k. And I can solve this for k. What I would do is to solve this by k is I want to get this square root bit alone. Actually, I'll do it a little differently, just for fun. I have this square root bit that I'm trying to solve for, so I'm just going to square everything. When I square everything, t becomes t squared. 2 becomes 2 squared, which is 4. Pi becomes pi squared. And the square root of m over k just becomes m over k. I can then multiply both sides by k to get it out of the denominator. And then divide both sides by t squared. And I'll get that the spring constant is 4 pi squared times m, which was 11 kilograms, divided by t squared, which was 0.8 seconds. Any questions? Okay, B is what is this max velocity? Where C is what's this maximum acceleration? I'm going to do both these at max at the same time. If I want to get Vmax and Amax, I have equations for those. See, you see, even though velocity is a function of time, the maximum value is always A omega. And the maximum value of A is always A omega squared. And so I can get both of these if I just solve for what omega is. To solve for omega, I have two choices. If I want to solve for omega, I can either say that omega is the square root of k over m, or I could use the fact that omega is 2 pi over t. It doesn't matter which one I use. I like to use 2 pi over t. Just because I'm not making a square root, I'm less likely to make a mistake. And I'll say omega is just 2 pi divided by 0.8 seconds. which is 7.85 radians per second. And now that I know omega, I can get V max, which is just 0.2 meters times 7.85 radians per second, which is 1.57 meters per second. And A max, which is 0.2 meters times 7.85 radians per second squared, which is 12.3 meters per second squared. These problems are normally not too complicated. You just have to know the relationship between all the terms. Questions? Okay. On the final, there'll either be a problem about springs, or there'll be a problem about pendulums, or there'll be a problem about both. I don't do both very often, though I have before. So that was a spring problem. Let's do a pendulum problem. And apparently I went very cartoony this chapter. And this problem is about Tweety Bird. And it says, Tweety Bird from Looney Tunes fame swings back and forth on his swing in his cage. He can be approximated as a simple pendulum with a period of 0.715 seconds. So, period is 0.715 seconds. How long is the pendulum? We're now looking at pendulums. So instead of looking at, the spring section, I'll look at the pendulum section. And I can see that for period, there's a direct relationship. That period is 2 pi square root of L over G. And so his period is 2 pi square root of L over G. And now I can just solve this for L. Now L is in the square root, so I'm going to kind of have to do the same basic idea as last time. Let's divide by 2 pi first. No real reason to do what order I do it in, but oops, I just forgot how to write an L. But I can divide both sides by 2 pi. And then I can square both sides. And if I multiply both sides by G, I can get an equation for L. And I get a value. Well, about 10 centimeters. About that long. That's not horrible. Part B. When Tweety swings, he goes a full distance from side to side of 10 centimeters. Okay, let's think about this. I'm saying when he swings, he goes from here to there. This value here is 10 centimeters. But of note, that's not the amplitude. Amplitude is the distance from the equilibrium to the side. If he goes a full distance of 10 centimeters, that means my amplitude is 5 centimeters, or 0.05 meters, because the amplitude is half of the full distance. Otherwise, though, it asks the same thing as last time. What's V max? Which is going to be omega A, just like last time. And what is A max? Which is going to be omega A squared, just like last time. And just like last time, I can solve for omega, because I can either say omega is the square root of G over L in this box right here, or I can go and use the same equation I did last time, that omega equals 2 pi over T, or 2 pi over 0.715 seconds, which is 8.79 radians per second. So 8.79 rad per second times 0.05 meters is 0.439 meters per second and 8.79 radians per second. Oops. I squared the wrong thing though. Squared times 0.05 meters equals 3.86 meters per second squared. Now you might notice this is basically exactly the same as the spring problem. Pendulums and springs are very similar. There's very little difference in the solving of the two different types of problems. Yeah, it's pretty straightforward. I could ask for some other things. I could ask for the frequencies, the frequency instead of angular frequency. I could talk about energy, but that's the general idea. Questions? One of my neighbors just started mowing the lawn, and it's just like, but it was snow this morning. Okay. Let's do the next problem. This next one is one of the weird problems where I actually did both springs and pendulums, but I think it has a kind of an interesting point. And I am going to color code this with blue and red. So it says the free fall acceleration on Mars is 3.7 meters per second squared. You see, on Earth, we have g, and g is 9.81 meters per second squared. But you see, on Mars, Mars has a different acceleration. G for Mars is 3.7. Only 2 sig figs? Only 2 sig figs. Okay. Which is kind of weird. And I'm not going to bother with subscripts, as I said. I'm just going to color code them. Everything in red is Mars, everything blue in Earth. And part A says, what length of pendulum has a period of 1 second on Earth? Well, we just did the pendulum equation. T equals 2 pi square root of L over G. I want to find a length when the period is 1 second. So just like before, I'll divide both sides by 2 pi, square both sides, multiply both sides by G. And I'll get, just like the last problem, T squared G over 4 pi squared. And so it'll be 1 second squared times G over 4 pi squared, which will be 0.248 meters. Just focused. Come on, focus better. Oh well. Part B says, what length of pendulum have a period of 1 second on Mars? See, if I want to get this from Mars, the logic is the same up to this line. I can still say L equals T squared G over 4 pi squared. But for Mars, I'm going to have to use the value of G for Mars, which is 3.7 meters per second squared. And I'm going to get a very different answer. I want this to focus just a little bit more. There we go. Now we're in focus. And yeah, pendulum would have a different period on Mars because of the fact that gravity is different. Part B. And you know what? Let's use green for Earth also. Earth is green and blue. It makes sense. Says, okay, let's say instead we have a spring constant that's 10 newtons per meter. How much mass has a period of 1 second? Well, for a spring, T equals 2 pi square root of m over k. So I can divide both sides by 2 pi, square both sides, and multiply both sides by k. And I'll say the spring constant will be T squared m over 4 pi squared. And I can plug in. What am I solving for k? Find the mass suspended. Actually, I hold on. I multiplied both sides by k. So this solved for m, and this was a k. Sorry, there was an algebra issue though. When I multiply both sides by k, the k goes up. So it's m equals t squared k over 4 pi squared. If I wanted to solve for k, it would just be just like what I did here, where I got 4 pi squared m over t squared instead. And so m will be 1 second squared times 10 newtons per meter over 4 pi squared, which will be 0.253 kilograms. Now, it says, what's the same thing for moles? Well, in moles, the only thing that's different is g is different. And if the only thing's different is g is different, g's not in here. In fact, nothing changed. So in moles, be the exact same answer without any change, because nothing else changed. Questions there? It's kind of crazy. The fact that the period of this has nothing to do with gravity. But once again, it's only really dealing with the force of the spring itself. What would change with gravity is that when it's stationary, where equilibrium is, that right now it's at this height, and Mars would be like up at this height instead, that it wouldn't stretch as much just due to gravity. But when it bounces, gravity has no effect. Okay? Another. This is not a problem I wrote. This is from a textbook, but I think the problem's just funny, so I like to cover it. And the problem is as follows. Someone is on a construction site where they have a wrecking ball. And so we got a big wrecking ball. And they're standing right here. And it says the wrecking ball, it has a length of 10 meters and is coming at them. And the question is, how long do you have to get out of the way before this thing goes, flying through, gets to the lowest point, and splatters you against it? Well, none of these problems really get into time. They get into period. You see, we have a question about the period of motion. But the period of motion is how long it would take the wrecking ball to go from here, across, and then back. I'm wearing green. Let's not use green. So go from here, across, and back. It's not talking about how long to get to the lowest point. That's something else. But the thing is, if we have this motion, we can actually just switch it over. Because what I can say is to go from one side to the other, that's going to be half the period. Because it's going from here to back to over. And if you think about it, going to the lowest point, that's actually a quarter of the period. Because here to straight down is 1 quarter, to this side is second quarter, here is third quarter, there's the fourth quarter. And so the time you have to not get smushed is just 1 quarter of the period. Now we know that the period is 2 pi the square root of L over G. And therefore the time you have, once again being the period over 4, would be 2 pi over 4 square root of L over G, which is the same as pi over 2 square root of L over G. And that'll tell us how much time you have. And you get 1.59 seconds. That's how long you have. After 1.59 seconds, smush. Okay. Any questions? Okay. Let's do one wave problem. The wave problem says a guitar string is 90 centimeters long. It has a mass of 3.8 kilograms. Sorry, 3.8 grams, not kilograms. 3.8 grams. And it's under a tension of 520 newtons. Now I'm going to write the tension as F. Just because tension is normally T, but capital T is normally period in this stuff, so it's just easier. And it says, what's the frequency? Well, if I want to find the frequency, I'm now looking at waves. And when I talked about waves, I only introduced these equations. And only one equation has frequency. Velocity equals frequency times wavelength. And if velocity equals frequency times wavelength, that means frequency is velocity over wavelength. And so I need two different things, neither of which I gave, velocity and wavelength. Let's start with wavelength. When I strum a guitar string, what happens when I strum this? Right? That when I go, is that this is bouncing back and forth. And if you look at the wave that's going, it's just going here to there, to there, to there, to there, to there, super, super fast and small. Well, a full wave looks like this. And that's not what it's doing. It's bouncing between here and there, back and forth. You see, the reason why is what I have is I have half of a wave. When you just strum a string, you have something where the wavelength is twice the length, which means my wavelength is 1.8 meters. So there's the number for lambda. As for V, well, I got an equation for V. V equals the square root of F over mu. Now to do that, I need to know mu, but mu is simply M over L. Well, in this case, 0.0038 kilograms over 0.9 meters. That value is 0.004222 kilograms per meter, which means V is the square root of 520 newtons divided by 0.004222 meters, which is 350.939 meters per second. And that's my V value. And now I can do that math and I'll get a frequency. And get that's a frequency of 195 hertz. Which, just so you know, 195 hertz is pretty close to a G. 196 hertz is a G. It's a little out of tune. Questions so far? Okay. Part B, though I don't think it actually names as B, is what is the frequency of the second harmonic? AKA if you lightly touch the string at the halfway point. Now, if you do that, if you lightly touch the string at the halfway point, it makes it so that lambda equals L. It does not change anything about V. And so my frequency is still V over lambda. And V is still 350.9 meters per second. It's just now my lambda is 0.9 meters. The reason for this is because if you lightly put your finger there, what you do is you cause a node at this point, and you get a full wave. And so my value is just going to be 390 hertz, which I didn't write down what note that is, so I don't think it corresponds to anything directly. Okay. Okay. That is not only the end of this chapter, but is also the end of anything mechanics. Everything we've been so far is called mechanics. We are physically moving things. We are physically strumming this string. The air molecules are moving. The last two chapters, which we're going to start on Monday, are going to be in thermodynamics. We talk about heat and temperature and what they mean. So we will start that up on Monday. I'm hoping by early on in the week I can tell you when the final exam is, and someone would tell me when the final exam is, since I still don't know. But I will send that information along as soon as I get it. I was hoping to get the information today, but no. Otherwise, though, we'll stop there. Have a good weekend, and I'll see you Monday.